The natural logarithm. Definition of the natural log function. Let's define a function named natural log, abbreviated by the letters ln, in such a way that for all positive x, natural log of x equals the integral from 1 to x of 1 over t dt. At this point, the name we've chosen for this function should be a mystery. A logarithm is the inverse of an exponential function, and it's not obvious that that is the case here. But we will soon learn that, in fact, this function has all the usual properties of a logarithm and is in fact the inverse of an exponential function. Now let's note that when x is greater than 1, the natural log of x is a positive number equal to the area under the graph of y equals 1 over x between 1 and x. When x is between 0 and 1, the natural log of x is a negative number equal to the negative of the area under the graph between x and 1. In fact, this function is always increasing, and its graph looks like this. It has an x-intercept at x equals 1. Its limit as x approaches infinity is infinity, that is, there's no horizontal asymptote, and its limit as x approaches 0 from the right is minus infinity. Actually, neither of these limits is completely obvious, but we will soon learn why they're true. This definition of the natural log is equivalent to the following two properties. First, note that natural log of 1 is equal to 0 because the integral from 1 to 1 of any function is 0 by definition. And second, its derivative with respect to x is 1 over x for all x greater than 0. This follows from the definition by the fundamental theorem of calculus. So in effect, we have defined a new function whose derivative is 1 over x for all x greater than 0. Let's look at a couple of example derivative computations. Let's take the derivative of x times the natural log of x. We'll use the product rule. The derivative of the first factor is 1, so we have 1 times the second factor, natural log of x, plus x times the derivative of the natural log of x, which is 1 over x. So simplifying gives us natural log of x plus 1. Now let's take the derivative of the natural log of cosine x. Here we need to use the chain rule. We'll take the derivative of the outside function, writing 1 over the inside function cosine x, and then multiply by the derivative of the inside function cosine x. So we have 1 over cosine x times the derivative of cosine, which is minus sine x. So we have minus tangent x. Algebraic properties. This is where we'll see that natural log of x has the usual algebraic properties of a logarithm. First, the natural log of a product x times y is equal to the natural log of x plus the natural log of y. The natural log of 1 over x equals minus the natural log of x. The natural log of x divided by y is equal to the natural log of x minus the natural log of y. And the natural log of x to a power p is equal to p times the natural log of x. We'll describe the proof of the first of these properties. Proofs of the other three will be similar. The way this is done is by showing that the two sides of the equation have the same derivative with respect to x, which tells us that they differ by a constant, and by showing that they have the same value at x equals 1, which tells us that the constant by which they differ is 0. So we'll differentiate the left-hand side with respect to x, with y treated as a constant. By the chain rule, this is going to be 1 over x times y times the derivative of x times y with respect to x, which is y. So we end up with 1 over x. Now let's take the derivative of the right side with respect to x. That's going to be the derivative with respect to x of the natural log of x, which is 1 over x, plus the derivative of the second term with respect to x, which is 0, because we're treating y as constant. Now let's look at the value of each side at x equals 1. When x is 1, the left-hand side is equal to the natural log of 1 times y, or natural log of y, and the right-hand side is equal to the natural log of 1 plus the natural log of y, but natural log of 1 is equal to 0, so we have 0 plus natural log of y, or log y. So for any positive y, the two sides of the equation have the same derivative with respect to x and the same value at x equals 1. Therefore, the two sides of the equation are equal for any positive x and y. Limits. Here we'll talk about some important limits involving the natural log function. The limit as x approaches infinity of the natural log of x is infinity. This is true because of the property that the natural log of x to the pth power equals p times the natural log of x, since that implies, for instance, that the natural log of 2 to the x equals x times the natural log of 2. This tells us that the range of the natural log function contains all positive numbers, since any positive number can be expressed as a positive number times log 2. That, together with the fact that the natural log of x is always increasing, proves that the natural log of x approaches infinity as x approaches infinity. Now, we can rewrite the limit as x approaches 0 from the right as the limit as x goes to infinity of the natural log of 1 over x, since as x goes to infinity, 1 over x approaches 0 from above. By one of the properties on the previous page, the natural log of 1 over x equals minus natural log of x, and since the natural log of x approaches infinity, this limit is minus infinity. So we've now justified the general character of the graph of the natural log. In particular, the y-axis is a vertical asymptote, and there is no horizontal asymptote. We'll state the next limit as a theorem. The limit as x goes to infinity of the natural log of x divided by x to the r is equal to 0 for any positive r. This statement is most interesting when r is small. It says that the natural log of x grows slower than any positive power as x goes to infinity. Now let's give a proof. Let's first choose p so that p is between 0 and 1 and greater than 1 minus r. Notice that if r is greater than or equal to 1, then that second inequality is automatically true if the first is true. Now, by the definition of the natural log of x, if x is greater than 1, then the natural log of x is the integral from 1 to x of 1 over t dt. Now, for all t between 1 and x, t will be greater than t to the pth power since p is between 0 and 1. That means that 1 over t is less than 1 over t to the pth power, and so the integral from 1 to x of 1 over t dt will be less than the integral from 1 to x of 1 over t to the pth power dt. Now let's evaluate this integral. T to the minus p power gives us 1 over minus p plus 1 times t to the minus p plus 1 evaluated from 1 to x, which is 1 over 1 minus p times x to the 1 minus p minus 1. Now let's divide the natural log of x by x to the r power. We know that the natural log of x divided by x to the r power will be greater than 0 since x is greater than 1, and now we also know that the natural log of x divided by x to the r will be less than 1 over 1 minus p times x to the 1 minus p minus 1 all divided by x to the r power, which equals 1 over 1 minus p times x to the 1 minus p minus r minus x to the minus r. Now, since p is greater than 1 minus r and r is greater than 0, both of the exponents here are negative. That tells us that as x goes to infinity, that quantity approaches 0, and so this proves that the natural log of x divided by x to the r also approaches 0 as x goes to infinity. From the limit we just proved, another important limit follows. The limit as x approaches 0 from the right of x to the r times log x is equal to 0 for any r greater than 0. To prove this, we'll first rewrite the limit as the limit as x approaches infinity of 1 over x to the r times the log of 1 over x. Next, we'll rewrite natural log of 1 over x as minus the natural log of x and put x to the r in the denominator. Now, by the previous result, this limit is just minus 0. Now let's look at some pictures to illustrate these two limits. Here's the graph of y equals natural log of x divided by x squared. Notice that the x-axis is a horizontal asymptote, since the function approaches 0 as x goes to infinity. Now, here's the graph of y equals the natural log of x divided by the square root of x. This function also approaches 0 as x goes to infinity, but much, much slower. Here's the graph of y equals x squared times the natural log of x, showing that its limit as x approaches 0 from the right is 0. Notice that the slope appears to approach 0 as well, indicating that the function values become very small very quickly as x approaches 0 from the right. Now here's the graph of y equals the square root of x times the natural log of x. This function also approaches 0 as x approaches 0 from the right, but so slowly that the slope approaches minus infinity. The function natural log of the absolute value of x. By composing the natural log with the absolute value function, we obtain a function that is defined for all x not equal to 0. Here's the graph of the natural log of absolute value of x for positive x, which is the same as the graph of the natural log of x. For negative x, the graph of the natural log of the absolute value of x is a mirror image of the graph of the natural log of x. Notice that natural log of absolute value of x is decreasing for negative x, so its derivative there should be negative. For negative x, the natural log of absolute value of x is the natural log of minus x, so its derivative by the chain rule is 1 over minus x times the derivative of minus x, which is minus 1, so we end up with minus 1 over minus x, or 1 over x. So it turns out that 1 over x is the derivative of the natural log of the absolute value of x for all x in its domain. This is especially interesting with regard to indefinite integrals. It means that the indefinite integral of 1 over x dx is the natural log of the absolute value of x plus c, a statement that's true everywhere in the domain of 1 over x. We can now state a power rule for integration that covers all exponents. The indefinite integral of x to the nth power dx is equal to 1 over n plus 1 times x to the n plus 1 plus c if n is not equal to minus 1, which we already knew, and if n is equal to minus 1, it's the natural log of the absolute value of x plus c. So we've now learned about the exceptional case in the power rule. Here's an example. Let's say we want to compute the indefinite integral of x plus 1 divided by x squared dx. We'll break the integrand up into two terms, x over x squared, or 1 over x, plus 1 over x squared. The first term, x to the minus 1 power, gives us natural log of the absolute value of x. The second term, x to the minus 2, gives us x to the minus 1 divided by minus 1, or minus 1 over x. And we add our arbitrary constant c. Now let's look at a few more examples. First, let's compute the indefinite integral of x divided by x squared plus 1 times dx. We'll make a substitution here of u equals x squared plus 1. We calculate du equal to 2x dx, and so the integral becomes 1 over u times 1/2 of du. We'll bring our 1/2 outside the integral, and now u to the minus 1 power gives us a natural log of absolute value of u times 1/2 plus c. Now we replace u with x squared plus 1. Notice that we don't need the absolute values here because x squared plus 1 is never negative. Another example. Consider the integral of tangent x dx. Let's write tangent as sine over cosine, and now we're going to substitute u equal to cosine x. That means that du is minus sine x dx, and so our integral is the integral of 1 over u times minus du. So here we have minus the natural log of the absolute value of u plus c, and we replace u with cosine x, and we've got minus log of absolute value of cosine x plus c. Now we can absorb the minus sign here by writing this as the log of 1 over the absolute value of cosine x plus c, or the natural log of the absolute value of secant x plus c. Another example. The integral of 1 over the square root of x times 1 plus the square root of x dx. Here we'll make the substitution u equals 1 plus the square root of x, which means that du will be 1 over 2 times the square root of x times dx. Fortunately, we have the extra square root of x in our denominator, and in fact 1 over the square root of x dx is equal to 2 du, so our integral now is that of 1 over u times 2 du, or 2 times the natural log of the absolute value of u plus c which is 2 times the natural log of 1 plus the square root of x plus c. Notice again that the absolute values are not necessary because 1 plus the square root of x can never be negative. The derivative of a composition of the natural log of the absolute value of x with another function u of x, with u of x the inside function, is by the chain rule 1 over u of x times u prime of x. So a derivative of this type has the very special form of a quotient whose numerator is the derivative of its denominator. Let's now write the equivalent fact about indefinite integrals. The indefinite integral of u prime of x divided by u of x dx is the natural log of the absolute value of u of x plus c. This is a very useful and important thing to remember. The natural log arises only when integrating a quotient whose numerator is the derivative of its denominator, or a constant multiple of it. For instance, consider the indefinite integral of cosine x over sine x dx, and the indefinite integral of cosine x over sine squared x. Let's make the same substitution, u equals sine x and du equals cosine x dx, in both integrals. Cosine x over sine x dx becomes 1 over u du, while cosine x over sine squared x dx becomes 1 over u squared du. Integrating u to the minus 1 gives the natural log of the absolute value of u plus c, while integrating u to the minus 2 gives minus u to the minus 1, not a natural logarithm. Now finishing these off, we have the natural log of the absolute value of sine x plus c, and minus 1 over sine x plus c. Again, notice that in the first integral, the numerator is the derivative of the denominator, and in the second integral, the numerator is not a constant times the derivative of the denominator. Logarithmic differentiation is a technique with which we can compute derivatives of functions that consist of an x-dependent base raised to an x-dependent power. A simple example is the function f of x equals x to the minus x power, whose domain we'll take to be all positive x. Here's the graph of that function. To compute its derivative, let's write the equation y equals f of x, or y equals x to the minus x power, and then take the natural log of both sides, rewriting natural log of x to the minus x as minus x times the natural log of x. Now we can differentiate each side with respect to x. On the left, we have 1 over y times dy dx by the chain rule, and on the right, by the product rule, we have minus 1 times the natural log of x plus x times 1 over x, or minus the natural log of x plus 1. Now let's multiply both sides by y to get dy dx equals minus log x plus 1 times y, but y equals the original function x to the minus x, so we finally have minus log x plus 1 times x to the minus x. So notice that there are 4 steps involved. First write y equals f of x, then take the natural log of both sides, then differentiate with respect to x, and multiply both sides by y and replace y with f of x. In the next lecture, we'll learn that the natural log function is in fact the inverse of an exponential function.